Gas mass flow process measurement is crucial for industrial processes like safety, quality control, and efficiency. Errors in measurement can lead to accidents, shutdowns, and increased costs. Therefore, to ensure accuracy, control systems like P, PI, and PID controllers are used to regulate flow effectively. The main objective of our experiment are determine the first order plus time delay model, calculate controller parameters for P, PI, and PID control, access control Assess control performance for flow indicator 91 using Ziegler-Nichols, Cohen-Kuhn, and internal model control (IMC) tuning methods. Simulated gas mass flow process is selected for our experiment. In our experiment, we identify the process variable PV limits is set to 0%, which is MV maximum, and 100%, which is MV minimum, and the obtained PV values at 80% and 75% MV settings. Controller parameters calculation were computed based on Ziegler-Nichols method, Cohen-Kuhn method, internal model control IMC method. The performance testing were done and based on our experiment, IMC, which is internal model control method, showed the best performance. The process variable quickly returned to the set point, which is the blue line, after a disturbance, indicating a quick and effective response.
Moving on to the second procedure, which is the process regression curve and also the controller parameter determination. So firstly, MV value was set to be 80%, and then the process was led to stabilize for a few minutes, and then the PV values were obtained, were tabulated in table 3.2, can be viewed. Then the above step was repeated with 75%, and the process was led to stabilize for a few minutes. And then first order plus time delay model was determined based on the graph obtained. Then the controller parameters were calculated for P, PI, and PID control using 3 different tuning methods based on the first order plus time delay model and tabulated in table 3.3, 3.4, and also 3.5. Good day, my name is Steven Mina. My metric card number is KA20008. So I'm starting with the methodology. So the first procedure is start up. Firstly, the gas mass flow process was selected at the operator workstation. Then the controller faceplate 91 was called up and the controller was set to manual mode. So once the maximum and minimum value for the process variable is set, the PV will check by setting the MV to 0%, which is the MV max, and the process was led to stabilize for a few minutes. After that, the table 3.1 process variable for the PV max was completed. So from step 3 to step 4 were repeated with MV minimum 100%. So the final procedure will be for the closed loop performance test. So firstly, the controller FIC91 was set to manual mode, and the controller was set based on P controller from controller tuning method 1, Cohen-Kuhn tuning. Then the set point was set to 18 kg per hour, and the MV was adjusted manually so that the PV fluctuated at the set point. The process was then to let stabilize for a few minutes. Then the controller FIC91 was set to auto mode, and set point change was simulated by changing the set point to 25 kg per hour, and then the process was led to be stabilized at a new set point. Then the graph was obtained from the results for discussion. So steps in task B were repeated for PI, PID controllers at lean using Cohen-Kuhn tuning method, and the graph of change was saved for discussion. So these steps were repeated for controller tuning method 2, Ziegler and Nichols tuning, and also the third one, internal model control tuning. The results were obtained for each controller performance and were discussed. So that's all from me. Thank you.
Assalamualaikum, my name is Farid Zati bin Saidi, metric ID KA20033. The purpose of this task is to determine the first order plus time delay model for a gas mass flow process and to calculate the controller parameter for PPI and PID controls using 3 tuning method, which is Cohen-Kuhn, Ziegler-Nichols, and IMC tuning method. The selected MV value is between 0% and 100%, and the corresponding PV is recorded. And we will determine the steady state gain, which is percentage of output at steady state divided by percentage of input at steady state, and we get a value of 2.377, and our time delay is T1 minus T0, which is 64 seconds, and our T constant is T2 minus T1, which is 9 seconds, and our response rate is Kp divided by Tc, which we get a value of 0.264 seconds, and our lambda is 0.9. We will go to our tuning method. For P we have gain, for Pi we have gain, reset, and for PID we have gain, reset, and rate. And here we can see the main difference between Ziegler-Nichols and Cohen-Kuhn is that Ziegler-Nichols provide a quick and straightforward method to tune PID controller.
Good evening, my name is Aldo Michael Santamara, and I'll be explaining about the results for internal model control, also known as IMC. So this table shows the equations that are used to calculate the gain, reset, and rate for the PI and PNID controllers. This table here shows the results that were obtained from the calculation for the gain, reset, and rate for PI and PNID controllers in IMC. Figure 1 shows the P controller for Cohen-Kuhn tuning relation. So from figure 1, the process value or the red line, it fluctuated in a sort of uniform pattern after disturbance was introduced. But however, it did not reach steady state. Next, for figure 2 for PI controller, the process value, it also reached a uniform pattern after disturbance was introduced. So after setting a new point of 25 kilograms per hour, the process value or the red line, it fluctuated as well, but it did reach a steady state in the end. Finally, for PID controller, the process value of the red line, it fluctuated in a uniform pattern. This was after introducing the disturbance. So after setting a new set point of 25 kilograms per hour, the process value it fluctuated as well, but it fluctuated non-uniformly and did not reach steady state. Next, figure 4 shows the P controller for Ziegler and Nichols. So from figure 4, it can be seen that the process value of the red line, it fluctuated in a uniform pattern after a disturbance was introduced, but it did not reach steady state. Figure 5 shows the PI controller. So the process value, it fluctuated in a uniform pattern after introducing the disturbance. So after setting a new set point of 25 kilograms per hour, the process value or the red line, it fluctuated but it reached a steady state in the end. Finally, for PID controller in Ziegler and Nichols, the process value or the red line, it fluctuated in a non-uniform pattern after disturbance was introduced, but it did not reach steady state as well. From this figure for PI controller for IMC, so the process value or the red line, it fluctuated in a non-uniform pattern after introducing disturbance. So after setting a new set point of 25 kilograms per hour, the process value of the red line, it fluctuated, but it did not reach a steady state. Finally, for PID controller, the process value fluctuated as well in a non-uniform pattern after introducing the disturbance. So after setting a new set point of 25 kilograms per hour, the process value is reduced in an amplitude, but it did not reach steady state in the end.
Based on the experiment, we find out the best tuning is actually IMC in comparison to Ziegler-Nichols, because Ziegler-Nichols is not ideal for rapid response needs, while Cohen-Kuhn has faster response but prone to oscillations. So it's not suitable for non-segregating processes. So why IMC is better is because they have near identical optical response for PI and PID controllers. It reduces the controller aggressiveness and short integral times. At the same time, it's so effective even though with inaccurate date time estimation, unlike the Ziegler-Nichols and Cohen-Kuhn. It minimizes oscillation and element overshoot due to the closed loop operation, and it has superior disturbance reaction which minimizes their impact onto the process. So how do I clarify the best tuning for the process? First, it should have minimal oscillation and overshoot. Why? Is to ensure a smooth and stable response to disturbance. And secondly is to swift return to the set point, where it helps to maximize the process efficiency and stability. So why IMC? Because it's the ability to handle uncertainty and achieve smooth and stable responses, and has high adaptability and resilience, which is potential for the improved control performance and reliability in various industrial and engineering applications. What is the function of doing this performance test? There's 4 factors, which is assessing the effectiveness, evaluating the response, optimizing controller settings, and validating simulation. So how is it is actually we are ensuring the chosen PID settings effectively regulate the system. That's why we're doing the performance test. Confirm the control system stability by verifying the set point tracking without oscillations, and we're alerting the response by testing the control reaction and assessing the control's handling, and optimizing the control settings by providing it the data and allows adjustment for the improvement. And lastly, we are also validating the simulations by comparing the accuracy within experimental results with the simulated predictions.
So as we know, this is an experiment that is conducted in order to analyze performance of PI and PID controllers using tuning parameters from 3 different aspects. And as the conclusion, we got IMC has the superior for controlling the gas mass flow process. Why this IMC is better, or what are the advantages of this particular IMC? It's because IMC can precisely account for process dynamics, which first leads to fastening the set point attainment under IMC tuning. And moreover, this can also enhance the steady state regulation by actually promoting a smoother process operation. So as we conducted our experiment, we found out that IMC can be the best controlling for the simulated gas mass flow process. Moving on to the recommendation. So this is the recommendation of our experiment. And first of all, this recommendation can be divided into 2 types, where I would say it's for process characterization and also for the stability test. So as for the process characterization, it is recommended to use graphing software for detailed examination, and also to carefully analyze the process reaction curve. Moreover, we can also estimate a precise estimation for time delay and also time constant. And as for the stability test, we can conduct comprehensive stability test and also introduce small set points adjustment during the occurrence of the experiment, and also to add additional disturbance to access the stability. So these are the few of the recommendation that we recommend in this particular experiment. And that's all from us. Thank you.